Okay, so the plan for today is to start chapter 5. So we finished up chapter 4, we finished up the material for the unit 1 exam, and we're going to be moving into chapter 5, systems of linear equations, and in particular starting with 5.1, solving systems of equations by graphing. And today we're also going to take a few minutes to discuss graphing on the TI-83 calculator. So how can we use the graphing utility in the calculator to help us with chapter 5? But also, this might be something that's helpful for chapter 4. Just a reminder, the Unit 1 exam is up and available. Lots of information that I mentioned about that last class and in the announcement. It is due this coming Tuesday, so you have the whole weekend plus a couple of days to complete it. And like I've mentioned a few times already, don't wait until the last minute or last day to complete the exam. Because the exam window is a week long, there's so much opportunity to take the exam. If you wait until the last minute, there are no due date extensions. It's not like the homework where you can just ask for an extension and have one granted. No due date extensions for the exam. So make sure to get it taken with a good bit of buffer or margin, just in case, if you wait until the last day and then something goes wrong with the technology, or something happens that you're not able to take it on time. That's a big chunk of your grade, so you don't want to risk that. And the quote of the day today is by a historical figure who was kind of, I guess he's a bit of a controversial figure, so I'm not going to give the attribution for the quote. But a scientist historically who said one physical test is worth 1,000 expert opinions. And this applies, I guess, more to my stats class, but it does kind of also apply to some of what we're doing in this class, where we're, say, building models to help understand the real world. And math folks and maybe physics folks, and we tend to have this bias where if something's a really nice mathematical model, if we can really cleanly see where each piece fits and where each piece comes from, we really like those models. But if we develop a model and somebody runs experiments, the experimental physicist runs some experiments, and the experimental evidence suggests that the model is wrong, then the model's wrong. So it's kind of unfortunate when that happens, when there's a really nice, clean theory and it's really elegant and simple in a sense, but it just doesn't match with what we see in the real world. So, for instance, see Newton's laws versus quantum mechanics, right? Quantum mechanics is crazy and messy. Newton's laws are simple and clean. But, it seems like the world works a little more like quantum mechanics than Newton's laws. Although in many situations, Newton's laws are a very good approximation. So no, don't get me wrong. That doesn't mean that we shouldn't look for elegance. That does tend to reward the one doing the research. If you could find a nice, simple, elegant solution, those tend to be maybe more likely to be right than some crazy complex solution. They also are much more easily built off of. If you have a simple answer, you can build the next level on top of that much more easily than if you have some big complicated model. So that's not that there's no value in the so-called expert opinion, but we always want to make sure that what we think is true is actually concordant with reality. Okay, so moving into chapter 5, we're in some sense starting a new chapter, but we're also going to see that this really relates back to some things we saw in chapter 3. So recall from chapter 3 these two problems, and there were several others like it, but I'm just using these two as examples. Remember, we had the example where we had some cooking vinegar and some cleaning vinegar that have different levels of acidity, and we would like to mix them together to make a certain amount, a certain number of fluid ounces of a solution that has a different acidity that's between those two acidities. So I can mix some of the 5%, some of the 7% to get a 6.2% acidity solution, and I want 30 ounces of that, 30 fluid ounces. And when we boiled everything down, we said we needed to solve these two equations. I needed to find A and B, the number of fluid ounces of the cooking vinegar and of the cleaning vinegar, respectively, such that A plus B is 30, such that the sum of the two volumes is 30, the total volume that I want, and such that the acidity combines the right way, that 0.05 times the amount of cooking vinegar plus 0.07 times the amount of cleaning vinegar equals 0.062, the desired acidity, times the total volume, the total amount of 30 fluid ounces. And so what we have is, instead of one equation and one variable that we want to solve, we have two equations and two variables. We want to find A and B to satisfy both of these criteria. So with one equation, or sorry, with one variable, kind of at the outset, if I just say pick X any way you want, you can kind of pick X to be whatever. But then if I say pick X any way you want, but it has to satisfy this equation, this linear equation, then kind of the standard result anyway is that there's a single value of X now that works. So when I have 1 degree of freedom, if it's matched with one constraint, when I have one thing I can choose, if it's matched with one criterion that needs met, that's kind of balanced in some sense. I can use that 1 degree of freedom, that one variable, to make the equation true, at least speaking kind of generally. Here I have two constraints I want to meet, a certain volume at a certain acidity. I need 2 degrees of freedom. I need two things I can choose to make those two true. So I can meet the volume and the acidity constraints by mixing two different fluids. And also last time we saw this example with the mixing the chicken and rice for a lunch to meet both a desired calorie need and a desired protein need. Same comments go for this one. We have two equations. We have 2 degrees of freedom, or two unknowns, two variables, two constraints, two variables. That's a balanced system. And I would expect to be able to find a solution to this. We'll see there are some special edge cases, just like there were in equations, some special edge cases like identities and contradictions of things. But at least typically we would expect that with two equations and two variables, we would expect to be able to find a solution. So we have two basic methods for solving these equations. One of them was the algebraic approach that we took. And there are even a couple sub-methods in algebraic that we'll talk about in the next couple of sections. But one thing we might do is we might say, well, if A plus B is 30, we can solve for A. And then if A is 30 minus B, I could swap in for this A, I could swap in 30 minus B instead, giving me one equation in one variable. So I go from a 2 by 2, two equations and two variables, down to a 1 by 1. I know how to solve this from back in chapter 2 when we talked about solving linear equations, and then I can plug back in. Right, so I can say solve for B, and then I plug back in to get A. If I get B is 20 fluid ounces, then A is going to be 30 minus 20, or 10 fluid ounces. So that was kind of the algebraic structure that we worked with. And we saw that we could do the same thing here, but it was just a little more complicated. This was kind of the challenge problem for the day last time for a review. But we also have something kind of new that we came up with in chapter 4, and that's the idea of being able to graph a single linear equation. So we might ask then, well, if I can graph a single linear equation and I can glean a lot of information from that graph, can I leverage this new tool, this new idea of graphing, to help me solve these systems of equations, to help me figure out what values of my variables will satisfy those constraints? And the answer is yes, and that's what we're going to talk about today. So what's the idea? Let's just kind of talk in the abstract for a minute, then move down and look at a specific example, and then move over to the calculator to look at how we can graph these on the calculator to get a little more accuracy, maybe a little more speed out of it, but definitely a lot more accuracy. So let's say that I have two equations, equation 1 and equation 2. And let's just say that we have something like y equals 3x and y equals negative x. I'm picking two simple equations here. Now I know that the equation y equals 3x has a bunch of possible solutions. I could list them in a table, for instance. But I can only list a selection of them in a table. And the same goes for equation 2. I can list some solutions in a table, but I can only list a selection of them. Something I could do if I wanted to is, instead of having a tabular representation of my relation between x and y, let's say for equation 1, I could instead have a graphical relation. I could come over here to my plot and I see, well, 0, 0 is a point on the line, and say 1, 3 is a point on the line. And that's equation 1. Or that's the graph of equation 1. This graphical solution is a visual representation of all of the solutions of y equals 3x. So this includes, for instance, 2, 6, maybe somewhere up here. It includes, for instance, -1, -3 down here, but it includes a whole lot of other points along that line also. And we mentioned that with this line, with this collection of ordered pairs, x, y, we can actually say that any solution of y equals 3x will be represented by an ordered pair on this line, and any ordered pair on this line will be a solution of y equals 3x. Now, what if I wanted to graph equation 2? I guess I could graph it on a separate plot, but I could also just use the same plot to graph equation 2 as well. I could just overlay the graph of equation 2 on top of the graph that I already have for equation 1. So equation 2 has a point 0, 0. It has another point on its curve, 1, -1. And this is equation 2. We see that we also have points like 2, -2, like -1, 1, and so on, right? So we pick another point or two, we check, looks good. And the same can be said about equation 2, that any solution to equation 2, y equals negative x, will be represented by an ordered pair on this line. And any ordered pair on this line, this blue line, is a solution to equation 2, y equals negative x. So now what if I changed my question around a little bit? And I said, find x and y to solve to simultaneously solve these two equations, y equals 3x and y equals negative x. Right, this is a very similar question to like find a and b to solve both of these two linear equations at the same time, or find c and r, the amount of chicken and rice, to solve these two equations simultaneously. Right, there's a bunch of amounts of chicken and rice that will get you the right calories, but might not get you the right protein. Or there's a bunch of combinations of chicken and rice that will get you the right amount of protein, but maybe not the right calories. And we suspect that there's just the perfect amount of chicken and rice that satisfies both at the same time. You get the calories and the protein both at the same time for that specific choice of chicken and rice. So what does that mean? It means that the XY combination I'm looking for, the ordered pair that I'm looking for, has to be a solution to equation 1. It must be on this line, the black line. And it also must be on the line corresponding to y equals negative x. It must be on the blue line as well. I'm looking for an ordered pair that is on both lines. So I need to find x and y to solve both equations simultaneously. In the graphical world, what does that translate to? Find a point of intersection of the two graphs. I'm looking for where these graphs intersect, where these two lines kind of share a common point. That point of intersection will be an algebraic solution. Why is that? Because that ordered pair is on the graph of equation 1, which means it's a solution to equation 1, but it's also simultaneously on the graph of equation 2, which means it's a solution to equation 2. So we have found an ordered pair that solves both equations for that same choice of x and y. Right? We can see that most of the, say, ordered pairs on equation 1 on its line are not also on equation 2's line. And most of the ordered pairs on equations 2 line, most of the x's and y's that solve equation 2, they're not on equation 1's line. They don't also solve equation 1. However, there's one special point. In this case, it's right here at the origin. It's not always at the origin. It's just, I just made a simple problem for us to work with. In this case, it's right here at the origin. At 0, 0. And I see that the ordered pair 0, 0 is on the line corresponding to equation 1 and the line corresponding to equation 2. I also note that 0, 0 is a solution to the two algebraic equations at the same time. So my solution is x equals 0 and y equals 0. If I plug in x equals 0 and y equals 0, that does simultaneously solve both equations. And I can see from the picture that no other ordered pair is going to be a solution to both equations at the same time. There are some ordered pairs that'll solve one equation, some other ordered pairs that'll solve one equation, but they never solve both at the same time. So this is the idea of solving by a graphical method. We'll plot the two lines for the equations on a graph, and then we'll search for a point of intersection between the two. Now, if we plot two lines, most of the time, if you just draw kind of two lines at random, if they're straight lines, most of the time we have exactly one solution. This is kind of our typical or standard case, but kind of similar to equations in one variable, we have some special cases. I could plot two lines, and they could happen to be perfectly parallel. If I have two lines that are parallel, there's a couple ways I can think about this. They're always the same distance apart. These lines here, they start out kind of far apart, but then they get closer together and closer together. But parallel lines are always the same distance apart from one another. They never get closer and closer together, so they're never going to intersect. Or I could think of parallel lines as being anytime that I move over to the right, say 1 unit, I move, in this case, down maybe 1.5 or 2 units. But the same correspondence goes over here. If I have these parallel lines that go in the same direction, if my buddy starts 100 feet east of me and we both travel north, and let's suppose the Earth is flat. So we'll just annoy all of the scientists and say the Earth is flat. We're never going to get any closer together, right? I guess on a spherical or roughly spherical Earth, we'd eventually converge at the North Pole. But if things were flat, then if somebody started, 100 yards east of me and we both traveled north, we just stay 100 yards away from each other. So if I have two parallel lines on my graph, what is my set of solutions going to look like? Well, I solve equation, let's call it 1, if and only if I'm on this line. I solve equation 2, if and only if I'm on this line. And the two lines never intersect. I can never solve equation 1 and equation 2 at the same time for the same choice of x and y. There's no ordered pair, x comma y, that's on both lines at the same time. So this actually has no solutions. And we have one other special case. So here I have equation 1. And then equation 2, when I graph it, it turns out to be the same line. So equation 1 and equation 2, when graphed, they turn out to be the same line. This could be something as silly as the algebraic relationship for equation 1 and equation 2 is exactly the same. You just have, whatever, y equals 2x plus 1 and y equals 2x plus 1. Well, pretty clearly, we don't really have two different equations here. But I could also just have a similar relationship, like 2y equals 4x plus 2. It doesn't look exactly the same, but you can see that all that I did was multiply both sides by 2. I know I can get an equivalent equation by dividing both sides by 2, and that would just give me my original equation. So these two equations are essentially the same equation from a graphing standpoint, or from a solution standpoint for that matter. And here I can say that any ordered pair that's on equation 1's line is also going to be on equation 2's line. So all of these and a lot more would be solutions. In this case, we have infinitely many solutions. So if we have two lines that are parallel and are the same line, we have infinitely many solutions. If they're parallel and are different lines, there are no solutions. And if they're any other configuration, if these two lines are not parallel, they're going to meet in exactly one place. There's no way that I can say have a system of two linear equations with two solutions or with five solutions. The only acceptable numbers of solutions are 0, 1, or infinitely many. We're either going to cross at one point, and at that crossing point, if we go to one side, we get further apart. If we go to the other side, we just keep getting further apart. Only one solution. Or we're parallel, where as we go left or right, we don't get any further apart or closer together. If we are parallel with two different lines, we have no solutions. If we're parallel with the same line, just repeat it twice, infinitely many solutions. Okay, so let's do a quick overview on graphing lines on the TI-83. Let me switch my share here. And let's just, as a warm-up, come up here to these two and graph them. So coming over to the TI-83, if you have something like an HP or a Casio or a different TI, the TI-84 will work essentially the same. If you have like a TI-89 or something, you can use those for the class. That's not a problem. But they just might work a little bit differently. You can either look up, say, a YouTube video or something on how your calculator works, or you can pop into office hours and I can help you out with it. But here, our calculator does all kinds of things like normal in this kind of standard home screen. But you might have noticed that up here, just under the window, there is this set of 5 buttons: Y equals, window, zoom, trace, and graph. So these buttons mostly control the graphing functionality of the calculator. So if I hit Y equals, let me clear some of this stuff out of there. That was from a different class. If I hit the Y equals button, the Y equals button is where I can enter the algebraic structure for my equations. If I look at my window button, that's where I can choose what window I want. Do I want to go -10 to 10 on the x-axis? Do I want to go, 1 to 7 on the y-axis? I can change my window here by changing x-min and x-max, y-min and y-max. I'd usually leave x scale, y scale, and x resolution alone. We have a zoom function. What this is nice for is there's this zoom square here. So if I'm graphing something like, say, a circle, maybe in MAT090, if I graph it on a funky window, it's going to look more like an oval. But if I graph it, get it kind of on the window where I'm kind of happy with it, but it kind of looks like an oval, and then I zoom square, the calculator will make adjustments to the axes so that it looks, so the circle will look like a circle on your calculator screen. You can see that the calculator screen is not like a 1-to-1 ratio of height to width. So things can get a little distorted, but zoom square will take care of that. Trace is something that, I click the button, there's nothing really to graph now, but what trace will allow you to do is it'll allow you to walk along this line. I'll just draw one up here. It'll allow you to walk along. If this is the line that I graphed, it'll allow you to select a point, and then it'll tell you the x and y coordinates, and you can move left and right and select different points. And then there's the graphing menu also that will draw the graph for you, or the graphing option that'll draw the graph for you. So let's try to graph y equals 3x. So we see there are a bunch of different lines here, y1, y2, y3, y4. These are for different equations. So I could graph equation 1, equation 2. If I had more of them, I could graph even more equations on the same screen. But here I just want to graph one equation. y1 equals 3 times x. So graphing y equals 3x. Just next to y1, I put 3 times x. It wouldn't hurt anything if you put it in y4 instead. It would look the same. I'm going to go to my window. What x and y axes do I want? Well, it looked like an x-axis of maybe something like -2 to 2. Might be a good place to start. And it looks like this is equation 1, the black line. So it looks like a y-axis of something like -3 to 3. Should also work. If I hit graph, I can see that I get a line that looks very much like the black line over here, equation 1. I could do the same thing for equation 2. I could just go down to the next line, y2 equals, and I want y equals -x. So I'll do -x. Remember to use the negative that's under the 3, not the minus sign that's next to the 6. So the minus sign has to have 2 arguments, something in front and something after. The negative just has 1 argument thing after it. And then if I go back to graph, I'll leave my window the same. If I graph, there's my second line. There's my equation 2. And one thing I could do is I could just look at this graph. I could look at it and visually estimate just from the calculator. Okay, I think 0, 0 might be a solution. And I can verify that when I plug it into the algebraic equations, 0, 0 is a solution for both equations at the same time. So I found a solution graphically. So what does the process look like? The process looks like get y in terms of x for both equations if needed. In this case, we already started out with y in terms of x. Enter the two equations into our y equals menu. Choose an appropriate window. And sometimes you choose a window and you say, oh, wait, the graph that I see looks like this, and I don't even see my other equation. Maybe I think my other equation is up here somewhere. So I might need to just adjust my window a little bit, right? So I might have a window like this that didn't quite work. So I say, okay, I think I need to go higher on the y-axis and maybe further to the right on the x-axis, and then I see my intersection. And then we graph and we get a picture, and from that picture we can maybe visually estimate what the solution is. If it's at an integer point, that's usually not going to be too terrible to estimate. If I wanted to zoom in on it a little bit, if I thought, is that 0, 0, is that like 0.1 comma -0.1, I could zoom in a little bit just by choosing a smaller x interval and a smaller y interval, say from -1 to 1 on both of those axes. So if I go back to my window, and if I choose x minimum -1, x maximum 1, y minimum -1, y maximum 1. So I'm graphing from -1 to 1 on both axes now. This is going to zoom me in a little bit. So now my left and right sides go from x equals -1 to x equals +1, bottom and top, y equals -1 to y equals +1, And I'm pretty confident that that's at 0, 0 now. Right. For linear equations, kind of when you zoom in or out, they kind of basically just look the same. So scaling doesn't really affect the look of linear equations very much at all. If we had something like say a circle plotted, if we zoomed way in, right, the circle would look a lot bigger. If we zoomed way out, it would look a lot smaller. But for linear equations, kind of if I zoom out, I'm just seeing a larger part of the lines, but they just still look the same, basically. Okay, so what would parallel lines look like? What if I had y equals 3 times x and y equals 3 times x plus 1? And let me adjust my window. Okay, I'm going to go maybe up to 3. So that's what parallel lines will look like. If I was suspicious, if I thought to myself, well, they look pretty parallel, but maybe I think that I see that it looks like the slopes are a little different. It looks like they're maybe coming together a little bit. I'm not sure. I could zoom out if I wanted to. Instead of -1 to 1 on the x-axis, I could go like, say, -10 to 10 on the x-axis. If I zoom out a little bit, any small amount of tendency to move toward one another will be amplified whenever I zoom out. I'll be able to see it a little better, maybe. I noticed when I changed x to go from -10 to 10, I didn't change y. And I noticed that I'm kind of running off the top and the bottom of the screen, so I need to adjust my y as well. Maybe I'll take y from like -20 to 20, see if that gets me a decent picture. And that looks pretty good. Now, something that can sometimes happen, like we saw here, is this graphing calculator, it's plotting pixels, right? It's trying to decide for each pixel, for each little dot that it's capable of displaying on the screen, should it turn that dot on or off? Sometimes we get artifacts like this. And if you're having trouble seeing this, let me try to screen cap it and move it over here. Oh, I tried to screen cap it, but then it didn't like. Anytime I hit shift, it switches it back. So unfortunately, I don't know if I can screen cap it because as soon as I hit shift, it switches it back, even if I'm holding the Windows key. Most programs are smart enough not to whatever to have a special case for the Windows key, I think. But anyway, so I can't quite screen cap it. But well, I wonder if I can do this. Can I take screenshot? There we go. That's going to be annoying. Okay, anyway, but I think you see on the picture that it looks like they're running parallel, and then all of a sudden they get a little closer together, and you think, oh wait, does that mean that they're actually not parallel? No, these actually are parallel, but this is just an artifact of how the calculator plots its points. It has to decide for each pixel, should it turn that pixel on or off? And sometimes, wonky little display things like this will happen. It's not that these lines aren't parallel, it's just that by zooming out so far, we're kind of forcing the calculator to make some decisions about certain pixels. It's trying to say, okay, is the line close enough to this pixel? Is the actual line close enough to the location of this pixel for me to turn it on? Or should I turn on an adjacent pixel instead? And it's just an artifact of the imprecision of the calculator that it looks like these two are approaching one another. So we need to be a little careful of that. We need to be cognizant of the fact that these graphs on a calculator are not 100% perfect all the time. They're usually much better than what we can do by hand. They're usually much more accurate, but they're not always going to be perfect. So if we zoom out too far, or then we kind of risk creating some of these artifacts and maybe misleading ourselves. But on a more reasonable window, we can see that it certainly looks like these are parallel. And if I was concerned about that point, whatever, where I thought they were going closer to one another, I could pick a window surrounding that point and investigate it, and I would get a picture that looks very similar to this one. Okay, so let's look at, oh, and then one more thing that I wanted to mention is, so going back to our example here, y equals 3x and y equals negative x. Remember that had the solution 0, 0. One other thing we can do, we can visually estimate the location of the solution. And if it's at an integer point or a point that's easy to estimate, we might be able to get it just by looking at the picture. So 0, 0 is easy enough to get just by looking at the picture. The other thing I could do is I could use the calculation menu. You see above where it says trace, it says calc. That's for calculation. So if I hit second, trace, that brings up my calculate menu. I can investigate, say, values or zeros where I cross one of the axes, or maxes or mins, or I can investigate an intersection between two lines. So that's what I'm going to pick. I'm going to navigate down to number 5, or just hit 5. I can either hit 5 or navigate down to 5 and hit enter, searching for an intersection. It asks me what's my first curve. So I see my first curve is indicated here as the one that goes from the bottom left to the top right. This y1 equals 3 times x, as it shows on the top left of the screen. I'm going to hit enter. I'll choose that as my first curve. Right. I could, in theory, have 4 or 5 curves plotted on this screen. So I have to tell the calculator which 2 curves I want to find the intersection of. Here's my second curve, y2 equals negative x. That looks right. So I'll hit enter. It asks me for an initial guess. For linear equations, it doesn't really matter. But if I had, more complicated 2 equations that say went like this, am I looking for this or that solution? Which intersection am I looking for? That's why the calculator asks for a guess. If I put my guess close to one of the solutions, it'll more likely find that solution. So in other situations, I might have 2 or 3 or 4 solutions. But in something like a set of linear equations, I'm only going to ever have one solution. So the guess doesn't really matter. I just hit enter again. And the calculator computes the intersection at 0, 0. So particularly if this was at a point that wasn't a nice point, if it was at 1/2, 3/4, this might be a nice thing to do. I could see the intersection at, say, x equals 0.5, y equals 0.75, and then that tells me, okay, that's 1/2, 3/4. Okay, so let's try to solve this system by graphing. And typically when we have a system of equations, we often write it inside of a curly braces like this. So we're going to graph this by hand, see if we can estimate the solution. And then we'll graph it by calculator, estimate the solution visually, and then use our intersection tool to find the intersection that way. Okay, so let's label our equations, equation 1 and equation 2. For equation 1, I'd like to find a couple ordered pairs to help me graph it. So I see when x is 0, y has to be 5. When y is 0, x is negative 5. And when x is something like what may be 2, y is going to be 5 plus x, or 7. I'm also going to get a few ordered pairs for equation 2 before I set up my graph, because I want to make sure that when I set up my axes that I set up my axes in a way that's going to let me graph both of them. So if x is 0, I have -2y equals -6, y is 3. If y is 0, and then I have 4x equals -6. That might not be such a good point to use. So in this case, I'll choose not to use the x-intercept. But if I had maybe x equals 1, 4x minus 2 equals -6, 4x equals -4, I think y is -1 there. Sorry, I did that backwards. If y was 1, then I have 4x minus 2 equals -6, 4x equals -4, x is -1. And what else could I have? Well, if x was 1, I have 4 minus 2y equals -6. If I subtract 4 over, -2y equals -10. And this gives me y equals 5. Okay, so let's try to plot these by hand. I'm going to try to be pretty careful with my plotting here because my goal is to find the intersection and visually estimate its location. So I'm going to try to make my axes pretty close to square. I'm going to try to make my tick marks along those axes pretty equally spaced, at least along x, and then equally spaced along y. The x spacing and y spacing, it's not crucial that those are the same, but the x spacing has to be consistent and the y spacing has to be consistent. And then I'm going to try to draw my lines pretty straight as well. So for the first line, maybe I'll draw the first line in blue. I have 0, 5. Well, so my y's have to go from what, 0 to 7. That looks like that'll take care of the second line as well. So I'm looking for 0, 5. That's here. For my x's, I need to go from -5 to +2. That'll take care of the second line as well. So I have -5, 0. I'll draw a line through these 2 points and try to do a pretty good job of it. And then does 2, 7 fall on this line? That does look pretty good. So I use this third point as a check. I'll graph equation 2. When x is 0, y is 3. When x is -1, y is 1. If I plot a line through and I get 1, 5, if I plot a line through these, it kind of looks like I'm going through 2, 7 here as well. So this does look good. So it kind of looks like I'm going through x equals 2, y equals 7. X equals 2, y equals 7 is a solution to the first equation. Is it a solution to the second equation? 4 times 2 minus 2 times 7, is that equal to -6? Or 8 minus 14 That's indeed is -6. So 2, 7 is an ordered pair that is on both lines, or x equals 2, y equals 7, does solve both equations at the same time. So I was able to find my solution graphically, even drawing the graphs by hand, if I'm pretty careful with drawing my axes and my tick marks for the units and all of that, and making sure that my lines are fairly straight. Let's do it on the calculator. Let's clear out all of our stuff in the y equals menu. Now the calculator wants the algebraic structure to be entered as y equals something. So I need to do a little bit of manipulation here first. I need to change my two equations to be y equals something. For the first equation, I can just add x to both sides. For the second equation, it's a little bit more complicated. I can subtract 4x from both sides. And then I can divide both sides by -2. -4 over -2 is 2. A negative over a negative is a positive, and 6 over 2 is 3. So the second equation took a little more work, but we get y equals 2x plus 3. And it doesn't matter which one I put into y1 or y2, or if I put one in y3 and one in y6. So it's not a big deal what order you have them written in or anything like that. But I'll put x plus 5 into y1 and 2x plus 3 into y2. And I'll start with a window from -10 to 10 on both axes. That's kind of a good standard default window to start with. So I have -10 to 10 for x min to x max, and also for y min to y max. And if I graph it, I see I get a very similar looking graph to what I got by hand. I note that there's one intersection on the screen up here in kind of the top right corner up in the first quadrant. And I see it looks like that might be, if I was visually looking at this, I might think that it's somewhere between like maybe x equals 2, maybe x equals 3, but about x equals 2. And the y is a little harder to tell, but maybe it's something like 6, 7, 8. So what I would typically do here is I would zoom in on that intersection that I see now. I would narrow down my search, maybe taking x from maybe 1 to 3, and y I thought was something like 6, 7, 8, something like that. So maybe I'll go from 5 to 10 on the y-axis, y min of 5, y max of 10, and then regraph. And I see my tick marks along the bottom here, x equals 1, 2, and 3. I have to kind of remember that, my x's were 1 to 3, and my y's were 5 to 10. So along the left side, I see 5, 6, 7, 8, 9, 10. For those tick marks, they're a little hard to see on the bottom and side of the screen. But if you're working with your calculator right in front of you, it's a little easier to see. But I can see that this intersection does really appear to be at x equals 2, right between 1, 2, and 3. And it does appear to be at this third tick mark up 5, 6, 7, 8, 9, 10. So it does appear to be at 2, 7. And if I wanted to verify that, I could do second calc, go into the calculate menu, hit 5 to select intersect. What's my first curve that I'm looking for? Y1 equals x plus 5. That looks good. My second curve, y2 equals 2x plus 3. That looks good. My guess. And it returns my intersection of 2, 7. It happened to, be using the point 2, 7 anyway for the guess, just because that's what happened to be in the middle of the screen. But we see an intersection of 2, 7, verifying again that what we got visually works. So for solving equations by graphing, we visually estimate a solution, and then we plug in and we make sure that it actually solves the algebraic equations, right? I mean, if I visually estimated this as 2, 7, there's nothing saying that it has to be at an integer point. It could be 2.1, 6.9. But in this case, it's right at 2, 7. I verified by plugging into both equations that 2, 7 is a solution to both equations. And that's my solution. Okay, so let's practice a problem here. So work on this problem, solve this system by graphing x minus y equals 2, 2x minus y equals 8. Take about 5 minutes to do this and try to do it a couple different ways. Try to carefully draw the graph yourself and find the intersection and make an estimate. Then verify that that estimate is correct by plugging into the both of the algebraic equations and making sure that it actually does work. And then jump over to your calculator, use the y equals menu and the graphing menu and visually estimate a solution on your calculator. And then also go through the calculate menu and find the intersection. So by hand, graph and estimate, confirm algebraically, and on the calculator, graph and estimate, and confirm with the calc intersect tool. So 4 things to do here. Take maybe 5 or 6 minutes to work through this, and then we'll come back and discuss it. Okay, let's work through this problem. So I found a couple of ordered pairs that satisfy each of equation 1 and equation 2. You could have used different choices, but for both of them, I used the x and y intercepts. They both worked out pretty nicely. And then I just found another third point to use as a check. I drew my graph, again, trying to keep my axes pretty square, keep my lines pretty straight, keep my intervals along each axis pretty consistent. I drew my blue equation 1 and my green equation 2. And I noticed that actually it seemed like the intersection was off of the original screen that I drew, the original set of axes. So I had to extend my x-axis over to the right a little bit, add a couple more tick marks. I had to add another tick mark going up my y-axis. And I visually estimated the solution at somewhere like 6, 4, x equals 6, y equals 4. So that was my tentative solution. That was my guess. Then I took x equals 6, y equals 4 and plugged into each of the two equations. 6 minus 4 is 2. That's correct. And 2 times 6 is 12, minus 4 is 8. That's also correct. So I confirmed then that x equals 6, y equals 4 is the solution to this system of equations. If I wanted to take a different approach, I could do a similar thing on the calculator. Now, to plug the formulas into the calculator, I need to solve for y. And in both of these cases, I can just add y to both sides and then subtract the constant over, giving me these two revised equations. Then I'll come over to my calculator. I'll type them in. Y equals x minus 2. And y equals 2x minus 8. The window that I'll choose, as I mentioned before, negative 10 to 10 on both axes, works pretty nicely to start with. And then we can zoom in as needed. So if I graph, I do see my intersection on the screen, so that's good. If my intersection was off the screen, I just have to adjust my axes until I saw it. I might be able to visually estimate from here, but that might be kind of hard. There's a lot of tick marks, and I don't really feel like counting them all. I think I'll narrow my search down to the first quadrant. So I'll let x go from 0 to 10, and the same for y. So this is the positive x's and positive y's. This is the first quadrant that I'm looking at now. 0 to 10 on both axes. And I see my intersection a little more clearly here. 0, 1, 2, 3, 4, 5. It looks like about x equals 6. And it looks like a height of about 1, 2, 3, 4, y equals 4. So my guess might be 6, 4. And if I do second calc, I'm looking for an intersection, so I'll choose option 5. The first curve, y1 equals x minus 2, that's correct. I'll hit enter. Second curve, y2 is 2x minus 8, hit enter. My guess, again, it doesn't really matter. I'll just hit enter again for wherever it puts the guess. And it does find the intersection at x equals 6, y equals 4, confirming what I got visually. Are there any questions on this problem? So this did take a while to do this one because we solved the same problem two different ways. We solved it kind of by hand going through this method and checking, and then we solved it on the calculator. So if you did both of those and didn't quite finish up at the end, that's okay. This was a longer problem because we were doing it both of those ways. Okay, so let's look at this system. 4x minus 3y equals 6, 8x minus 6y equals 17. Why is it not letting me select different colors of pens now? Let me restart OneNote here. There we go. I don't know what that was about. Okay, so looking to solve this system. And just like before, I'll have equation 1 and equation 2. I'll be looking to graph each of these. So let's see if x is 0 in equation 1. If x is 0, negative 3y equals 6, y has to be negative 2. That's not too bad. If y is 0, 4x equals 6, I think that's going to be annoying to deal with. What else could I have? Maybe if x is, well, if x was 2, I'd have 8 minus 3y equals 6. If x is 3, 4 times 3 is 12. 12 minus 3y equals 6. I think y is 2. So 12 minus 6 would be 6. So that gives me 2 points on the line. So it gives me 2 points on line 1. What about finding 2 points on line 2? 8x minus 6y equals 17. Unfortunately, this combination of x and y is, there's going to be no nice combination of x and y because the left-hand side is always going to be even, the right-hand side is odd. So we're just going to have to bite the bullet here a little bit. And what do we get? If x is 0, let's say, then y is negative 17/6. Not a very nice intercept to deal with. If y is 0, what's x? 17/8. Also not super nice to deal with. So I think for this one, instead of doing it by hand, I'm going to do it on the calculator, right? These 2 points aren't too bad to graph. 0, negative 2. And 3, 2. That's not too bad. But I don't think I'm going to get very nice numbers out of equation 2. And keep in mind that, when we were just getting a graph of a line, it wasn't that big of a deal if we had some imprecision. We were just trying to get the general kind of shape of the line. Did it look like this, kind of cutting through the first quadrant, or did it look like this or something? But here we really need a little bit more precision because we're using the graph to get a visual estimate of the solution. So I think in this case, graphing by hand is going to be really difficult. I would have to be really precise to be able to get line 2 graphed accurately enough that I can make a good estimate of what's going on. So let's lean on the calculator a little more heavily here. Right, I probably could do it if I really wanted to, but it would require a lot of work to do this by hand. So for the calculator, again, I need to put this into the form y equals something for each of these. So let's solve equation 1 for y. So what can I do? I can subtract 4x from both sides. And then divide by negative 3. So negative 4 over negative 3 is 4/3. And then 6 over negative 3 is minus 2. This is equation 1. Y equals 4/3 x minus 2. Equation 2, I do something similar. I subtract 8x over. I divide through by -6. So this gives me 8/6 x, the negatives cancel, minus 17/6. Or I can simplify that 8/6 to 4/3. So this is equation 2. All right, let's put these in the calculator. So 4/3 times x minus 2 for equation 1, and 4/3 times x minus 17/6. That's equation 2. I'll go back to my window and change my axes to be -10 to 10 again for both of them. Again, that's just usually a pretty good starting point. Usually that's a big enough window that you'll see most of the interesting stuff going on. And then you can narrow your search if you want to. So x min to x max, -10 to 10, and same for y min to y max. And I'll go over to graph. And here I have two lines that seem to be parallel and are not the same line. Let me zoom in a little bit, maybe in just kind of more or less the middle here, but a little off to the right. So maybe like -2 to 5 on x, and maybe about the same for y. There's nothing super special about -2 to 5. I think that'll just get me zoomed in quite a bit, so I can really investigate whether I think these are parallel. And that looked to be a window that would keep both of my graphs in the picture. And these do definitely seem to be parallel. One way that I can tell that these are parallel, and this gets a little bit into slope. We didn't cover slope in chapter 4. At CCAC, the way that we have designed our algebra courses, we don't cover slope until 108. But this gets a little bit into the idea of slope. If I go over 1 unit in x, if I add 1 to x, then y is going to increase by 4/3 in equation 1. And likewise, if I add 1 to x, y will increase by the same amount in equation 2. So if I move myself from, say, x equals 2 to x equals 3, then y will increase from whatever it was to 4/3 more in both cases. So because the coefficient of x is the same in both cases, these are parallel lines. Or another way we can see that they're parallel lines is we could have divided equation 2 by the number 2. Just get rid of those. I could divide equation 2 by 2, divide equation 2 by the number 2, to get an equivalent equation to equation 2. That's 4x minus 3y equals 17/2. I noticed that my relationship between x and y is the same between equations 1 and 2. I have the same left side, but a different right side. I've kind of changed the problem around a little bit to an equivalent problem where I can see very clearly that if there was an x and a y such that 4x minus 3y equals 6, if there was an x and a y that solves the first equation, it cannot solve the second equation. If it solves the first equation, 4x minus 3y has to be 6, but 4x minus 3y cannot then also be 17/2. Or if it solved the second equation, if I chose such an x and a y that 4x minus 3y equals 17/2, and I get a solution to the second equation, it cannot solve the first equation because 4x minus 3y has to be 17 halves, not 6. There must be no solution here. So a couple of things, maybe 3 things to take away from this problem. Sometimes, even if you want to solve a problem by hand for whatever reason instead of the calculator, sometimes it's just extremely cumbersome and we just go to the calculator. There are other times, like maybe for instance, this problem up here, y equals 3x, y equals negative x, where the hassle of plugging everything into the calculator, getting the window set up, doing the graph, finding the intersection and all of that, is it really worth that time spent to use that tool on such a simple problem? No, you just graph this one by hand. It's going to be much quicker. So some problems are a little more amenable to the calculator, some to doing it by hand. In this case, it was still a bit of work to do it by the calculator. But I don't think we would have been able to graph accurately enough by hand to really see that those 2 lines are actually parallel. The second thing to think about is this kind of idea of the relationship between x and y. In a system like this, there's no way that I can make the x's and y's, their relationships look the same for both of these equations. If I tried to do that, if I tried to say, okay, well, maybe if I multiplied equation 1 by -4, that would make the x parts look the same, right? So what would equation 1 turn into if I multiplied both sides of equation 1 by -4? I'd have 4x minus 4y equals -20. I've got the x bits looking the same, but the y bits don't look the same, right? Even if I try to manipulate this to say make the x terms look the same, I see I get different y terms. Or if I made the y terms look the same, I'd get different x terms. The relationship between x and y is different between these 2 equations. Or that means whenever I say add 1 to x, what change do I have to make to y in order to keep the point on the line? It needs to be a different change for equation 1 versus equation 2. How much I have to increment y when I add 1 to x. If the 2 sides end up looking the same, that means when I add 1 to x, I need to make the same change to y in both cases. That means they're just tracking right alongside each other. So here we got the special case of no solution. And then the third thing we can do to kind of check a no solution type answer, you might say, like, up here, I mean, I got a candidate solution and I checked that it was correct by plugging in. So that acts as a check. How can I check a no solution? I can make my XY relationship look the same as one another between the 2 equations. That has to be the case if we have a no solution result. If I make those X and Y relationships look the same, then if there was a solution, since 4x minus 3y is in both cases, I would be effectively claiming that 6 equals 17 halves, and of course that's not true. So this has to be a contradiction. If I claim that there was an XY coordinate that solves the first one, it cannot solve the second one, and vice versa. So let's take a look at this next problem over here, and I will give you a heads up that this is a special case, similar to the one we just did. But it's not going to be exactly the same as the one we just did. So take maybe 4 minutes or so on this one and try to tease out what's going on here. And then we'll come back and we'll discuss it in about 4 minutes. Okay, so let's take a look at this one. So hopefully you realized whether you either solve for y in terms of x to use the calculator, in which case you would have gotten the same y equals stuff, you'd have gotten the same stuff for both of the equations. Or if you started out maybe writing on a table of values, you might have realized that we get the same solutions. We get the same table, the same xy coordinates for both equations 1 and 2. These just represent the same line. These are just different ways of saying the same thing. We don't really have two independent criteria here that we have to satisfy. This is really just the same criterion written twice. So if I were to take my second equation and divide by -2, I see that would give me an equivalent second equation of 3x plus 4y equals 8, but that's exactly the same equation as the first one. This is really just saying the same thing, giving the same single criterion 2 times. Since this is the same line that goes through, for instance, 0, 2, and what was another point, -4, 5. And we don't have to be accurate here. Any point on this line represents a solution to, say, equation 1, but also to equation 2 because they're the same line. There are infinitely many solutions. For instance, 0, 2, x equals 0, y equals 2 is a solution to the system, as is 2, 1/2, or 4, -1, or -4, 5, or any other point represented by this line. These are the same line. We have infinitely many solutions because we have two variables, 2 degrees of freedom, 2 things to choose, and we only have one constraint. That leaves us 1 degree of freedom. That leaves us one free choice that we can make any way we want. We can choose x to be whatever number we want, and then just solve the resulting equation to figure out what y has to be. We get infinitely many solutions, and if we had graphed these two equations on the calculator, it would have plotted this one, and then it would have just seemed like your calculator stalled, but really what your calculator is doing is it's plotting the second line directly back over top of the first one. So it would have just kind of sat there for an extra couple of seconds. You wouldn't have seen anything change, but it's just plotting the second line, turning on all of the pixels that are already turned on. Any questions so far? Oh, wrong one there. Okay, let's we'll maybe finish up a couple of these problems next time. But let's quickly look at, let's say, for instance, this vinegar question and see if we can get a solution using the calculator for this problem. So here I'm going to rephrase this as x plus y equals 30. So here x is going to be the cooking vinegar and y the cleaning vinegar, the amounts, and 0.05x plus 0.07y equals 0.062 times 30. I'm going to lean on my calculator here because these numbers don't seem super nice. I need to solve for y in terms of x in both cases. My first equation is not too bad, y equals 30 minus x. My second equation, what do? I subtract 0.05x over. Let me figure out what's 0.062 times 30. If I want to get out of the graphing utility, I just do second quit. So this gives me 1.86. And I subtract 0.05x over, and then I divide by 0.07. It's not very nice, but I'm going to leave my equation in this form rather than simplifying or like getting approximations. I'll go into my y equals menu, enter these two equations. So 30 minus x and 1.86 over 0.07 minus 0.05 over 0.07 times x. That looks right. I'll go to my window, and I know that x has to be between 0 and 30. Right? The amount of cooking vinegar that I use has to be between 0 and 30 fluid ounces, as does y, the amount of cleaning vinegar. So I'll set my window 0 to 30 on both of those, just because from the context of the problem, that's sensible. I'll graph. And I see my intersection on the screen, so I'm happy with that. That means that I have a solution in the math sense and in the vinegar sense, but I have a solution that's reasonable. I don't have to use like a negative amount of one of the vinegars or something like that, right? I can find my solution by doing second trace to get to the calculate menu, 5 to find an intersection. The first curve, y equals 30 minus x, yep. The second curve, this long, messy looking thing. The guess, I'll just hit enter again. And I see my intersection is x equals 12, y equals 18. So I want to use 12 fluid ounces of cooking vinegar, 18 fluid ounces of cleaning vinegar. And leaning on the calculator for these messy calculations was, I think, a heck of a lot nicer than when we worked through this by hand, right? That was a bit of a messy algebra problem to solve, but the calculator solved this messy problem with all of these crazy decimals and everything. It solved it just as easily as it solved this almost trivial problem up here. So the calculator, it's pretty much the same amount of effort and work for any problem solving by hand, in this context anyway. Solving by hand, sometimes it can be super quick, sometimes it can be super tedious, or anything in between. All right, so that wraps us up for today. We'll kind of finish up another problem or two next time, and then we'll start talking about algebraic solution methods. So what are some methods that we can use to solve these systems of equations directly algebraically instead of using the graph? Okay, I will see you all next week. Have a great weekend.